SpaceX just dropped a bombshell in space exploration. What if I told you there's a brand new way to send Starship all the way to the moon without any in-orbit refueling? Sounds impossible? Think again. In today's Techmap episode, we're uncovering a forgotten rocket from the 1960s that inspired SpaceX's latest breakthrough, the key to launching moon missions faster, cheaper, and with way less complexity. Stick around because this could change the entire game for how humans return to the lunar surface, and it's happening right now. The countdown to Starship's 10th flight is on, and excitement across the space community is hitting new levels. Flight 10 is shaping up to look a lot like Flight 9. We'll see a controlled booster splashdown attempt, the release of Starlink satellite simulators, and even more experiments to push this giant rocket one step closer to being ready for the moon and Mars. But here's where it gets interesting. Flight 9 already tried to complete the objectives originally assigned to Flights 7 and 8, both of which failed. So in a way, SpaceX has been carrying unfinished business for 3 missions now. If the third time wasn't the charm, will the fourth time finally be the breakthrough? The stakes couldn't be higher. SpaceX is under massive pressure because time is running out. NASA's Artemis 3 mission, which will send astronauts back to the moon, is officially scheduled for mid-2027. Between now and then, SpaceX has a mountain of work ahead. At the top of the list is finishing Starship HLS, a special version of the rocket designed for lunar landings. This spacecraft has one job: safely take 2 astronauts from lunar orbit to the surface of the moon and back. Sounds simple, but to get there, SpaceX has to prove the basics first. That means mastering orbital insertion, in-space propulsion, and re-entry. And the only way to do that is with multiple Starship flights. Each launch makes the system more reliable, and reliability is exactly what they'll need as they develop Starship version 3, the one that will test in-orbit refueling, a technology absolutely critical for Artemis 3. And then comes the real proving ground: the uncrewed demo mission. NASA requires SpaceX to land a Starship HLS on the moon and bring it back to orbit without astronauts on board before any crewed mission can happen. That test has to nail precision landings within 100 meters, surface operations, and ascent. NASA's own analysis even warns there's a 1 in 3 chance the lander won't be ready before late 2026. That means SpaceX has to move faster than ever to hit the 2027 deadline. Finally, there's the most difficult challenge of all: in-orbit propellant transfer. This has never been done in spaceflight history. SpaceX already made history in March 2024 with their first propellant transfer demo. But turning that into a repeatable, reliable system is a whole different game. So here's the big question: can Flight 10 set SpaceX on the right track to deliver all of this in time for Artemis 3? Or are we about to see the pressure hit its breaking point? At this point, some people might ask, why not just skip the complexity of orbital refueling altogether? Wouldn't it be easier to build a rocket powerful enough to fly straight to the moon in one shot? Well, that idea isn't new. In fact, it takes us back to a forgotten chapter in rocket history: the Nova rocket. Back in the 1950s, as the United States Air Force worked on the mighty F-1 engine, NASA dreamed of something even bigger than Saturn V. Their bold vision? A launch vehicle capable of direct flights to the moon, no orbital assembly, no separate lander, no rendezvous, just one giant rocket carrying everything in a single shot. That rocket was called Nova. Nova was designed to be an absolute monster. Standing only slightly taller than Saturn V, it was much wider, giving it room for more engines and heavier payloads. The first stage was an enlarged version of the SIC, powered by 8 F-1 engines. Meanwhile, the Saturn V rocket's first stage is powered by 5 F-1 engines. Above that, a second stage with 8 J-2 engines, And finally, a stretched SIVB third stage would push the spacecraft all the way to the Moon. In this configuration, NOVA could deliver 210 tons to low Earth orbit, or an incredible 74 tons directly into lunar transfer orbit. With that kind of muscle, NASA could have attempted a direct landing on the Moon. No docking, no refueling, just a continuous flight from Earth to the lunar surface. So why didn't NOVA ever fly? Ironically, it wasn't the rocket science that stopped it. The problem was the factories. The Michoud assembly facility simply wasn't tall enough to build a 12-meter-wide monster rocket. At best, they could fit 4 or 5 F1 engines inside a 10-meter diameter core. Expanding the facility wasn't realistic, not with the tight timeline of the space race. By the early 1960s, NASA had shifted focus. Saturn V, with some modifications, could already deliver what was needed. And with the Apollo program on the clock, there was no time for brand new rockets. By 1964, NOVA was quietly canceled, its promise of direct moon landings buried under a new vision of the future: reusable space planes and eventually, the space shuttle. In other words, NOVA was the path not taken. Humanity chose orbital rendezvous and smaller rockets instead of brute force mega rockets. Anyway, if you loved this deep dive, smash that like button, hit subscribe, and ring the bell. We're aiming for 150,000 subscribers, and we need you to get there. And now, 60 years later, the same question returns. Could SpaceX pull off what NOVA never did? Could Starship evolve into a direct-to-moon vehicle, skipping the orbital refueling hurdle altogether? Or is refueling in space simply the only practical way forward? Technically, NOVA and Starship actually share some striking similarities in their ambitions: to lift enormous payloads and to make the Moon within reach. On raw power, Starship leaves NOVA in the dust. NOVA's first stage, with its 8 F1 engines, was expected to produce about 62,000 kilonewtons of thrust. Impressive for the 1960s, but today, Starship's Super Heavy booster cranks out 73,500 kilonewtons from 33 Raptor engines. That's the most powerful rocket stage ever built, beating even the dreams of NOVA's designers. The upper stages tell a similar story. Starship's second stage, powered by 6 Raptors, delivers more thrust than NOVA's upper stage could ever manage. True, NOVA had the edge in specific impulse thanks to the J2 engines, but with SpaceX's vacuum-optimized Raptors, the gap narrows dramatically. Where Starship does stumble is mass. Its dry weight is higher than NOVA's envisioned upper stages, partly because it's built as a fully reusable spacecraft, with heat shields, flaps, and structural reinforcements. But here's the twist. In the lunar lander version, where the heat shield and re-entry hardware are stripped away, the weight drops significantly. SpaceX could, in theory, shave off even more by switching back to carbon fiber construction, though that would come at a much higher cost. So in many ways, Starship is the spiritual successor to NOVA, a machine designed to move mountains, not just payloads. The difference? NOVA never left the drawing board. Starship, on the other hand, is already flying, and with every launch, it inches closer to achieving the direct lunar access that NOVA once promised. Additionally, to make the concept of NOVA Starship work, Starship would need some major changes. First, it would have to sacrifice reusability. Right now, Starship is designed to always save fuel for a controlled landing back on Earth. But for a direct flight to the Moon, every drop of propellant would be needed just to get there. In other words, no fuel left for the return trip. Starship would become a one-way vehicle. Second, SpaceX could add a third stage. The original NOVA rocket had 3 stages, and the same concept could be applied here. Imagine a compact third stage tucked inside Starship's cavernous payload bay, providing the final push into lunar transfer orbit. That would give Starship NOVA-like capability without redesigning the entire rocket. And the benefits of this NOVA Starship approach are clear. The biggest bottleneck in Artemis right now is orbital refueling. It's unproven, it's complex, and it could take 10 separate Starship launches just to fuel a single lander in orbit. Every delay compounds the risk of slipping further behind schedule. By cutting refueling out of the equation, SpaceX could dramatically accelerate lunar missions. No worries about cryogenic fuel boil-off, no giant orbital depots, no risky fluid transfers in zero-G. Just a single direct shot to the moon. The same simplicity that made Nova such a compelling idea in the 1960s. In the short term, a Nova-inspired Starship could give NASA and SpaceX a fast, practical path to keep Artemis on track, while still working toward the harder technologies of tomorrow. However, long-term, in-orbit refueling remains the holy grail for deep space travel. So, why orbital refueling is a total game-changer for deep space exploration? Here's the deal. If a spacecraft can top off its fuel tank in low Earth orbit and gain an extra 9 kilometers per second of delta V, that's a fancy way of saying rocket speed boost. It suddenly gains the power to reach anywhere in the solar system. We're talking Moon, Mars, even the outer planets and their moons. This tech means spacecraft no longer have to carry mountains of fuel from Earth, which limits how much cargo or people you can send. Instead, smaller launch rockets can put spacecraft in orbit, and then those spacecraft refuel and zoom off to wherever humanity wants to explore next. What about military and strategic advantages? Now, the military is paying close attention too. The Defense Innovation Unit is teaming up with SpaceX to explore how Starship's refueling capability could be a huge advantage, not just for NASA, but for broader defense and strategic operations in space. Gary Henry, a senior advisor at the Defense Innovation Unit and former SpaceX exec, put it like this: being able to maneuver in ways your adversaries can't, that's a decisive edge in any orbital conflict. Imagine being able to position your spacecraft anywhere needed, refuel, then strike a strategic orbit or mission no one else can match. Okay, now let's talk about a vision. Straight out of sci-fi, orbit gas stations. Here's the cool part. This isn't just theory. Back when Henry was at SpaceX, the company already saw Starship as a potential gas station in space. That means instead of launching every spacecraft with huge, bulky fuel tanks, which adds weight and cost, vehicles could launch lighter, fly to orbit, and then refuel to continue their missions. Think about the possibilities. Longer deep space missions, more flexible exploration plans, and of course, big savings on launch costs. Plus, this system can support diverse missions, scientific, commercial, and military, all benefiting from orbital refueling. NASA will not beat China to the moon. Unless something changes, it is highly unlikely the United States will beat China's projected timeline to the moon's surface. Those aren't the words of casual observers. They come from major NASA political figures, including former Congressman Jim Bridenstine, the architect of the Artemis program back in 2019. It paints a sobering picture. America's ambition to reclaim dominance in the space race is colliding with a harsh reality. China's space program is advancing rapidly on all three critical fronts of its lunar strategy: the powerful rocket to send astronauts into lunar orbit, the spacecraft to carry the crew, and the lander to ferry them down to the surface and back. On August 6th, the China-manned space agency achieved a milestone by testing a high-fidelity mock-up of its massive 26-ton Lanyu lunar lander. This wasn't just another trial run. It was the first time China demonstrated extraterrestrial landing and takeoff capabilities for a crewed spacecraft, marking a pivotal leap in its lunar exploration roadmap. Soon after, the agency, working with the state-run China Academy of Launch Vehicle Technology, pulled off another feat: a successful 30-second test fire of the Long March 10 rocket's core stage. powered by 7YF-100K engines burning kerosene and liquid oxygen. This rocket is designed to fly with 3 such cores strapped together, capable of hauling 70 metric tons into low Earth orbit. And the progress doesn't stop there. Just weeks earlier in June, China tested the launch escape system of its new Mengzhou spacecraft, another crucial step in preparing a vehicle destined for lunar missions. The pace of progress makes it increasingly likely that China could achieve a crewed moon landing before the decade closes. To make all this progress possible, China's lunar program is following a deliberate crawl-walk-run strategy, which is like learning new skills step by step before doing big things. On top of that, China can study and learn from the experience of its rivals, especially NASA, which landed humans on the moon nearly 60 years ago during the Apollo program. Much of NASA's data is publicly available, offering valuable insights. Still, China must design, build, and operate its own spacecraft. Meanwhile, NASA emphasizes that Artemis isn't just about repeating Apollo. It's about pushing further with new, more sustainable technologies. The problem? Artemis hardware, like SpaceX's Starship HLS that relies on complex in-orbit refueling, is running into serious delays. Earlier this year, 3 consecutive Starship test flights ended in explosions, clear signs that it could be several more years before these cutting-edge technologies are truly ready for action. On paper, the United States holds clear advantages: a larger economy, decades of spaceflight experience, and an established space industry capable of reusable launches. But what it lacks is the stability to consistently pursue the same goal over time. Political shifts often derail long-term plans. Under Trump's first term, the target was to land astronauts on the moon by 2024. Now, halfway through 2025, that goal has slipped. In Trump's second term, priorities seem to be swinging yet again, this time between returning to the moon and setting sights on Mars. China, by contrast, operates with a steady and systematic approach. Their space program doesn't lurch from one vision to another with each leadership change. Instead, they pursue their goals with persistence and long-term stability, both in terms of budget and strategy. It's not just Bridenstine sounding the alarm about NASA falling behind China in space. Respected China analyst Dean Cheng voiced a similar concern, warning, "At the rate things are going, sadly, it seems quite likely that the Chinese will land on the moon before NASA can return to the moon." Their comments raise bigger questions, not only about who will step on the moon first, but also about how often. Will the U.S. manage just a handful of missions, while China makes going to the moon a regular occurrence? Still, is the situation really that dire? Acting NASA Administrator Sean Duffy is carrying the banner of optimism. In an all-hands meeting with NASA employees, he pushed back strongly. "We had testimony that said NASA will not beat China to the moon. That was shade thrown on all of NASA. I heard it, and I gotta tell you what, maybe I am competitive. I was angry about it. I can tell you what, I'll be damned if that is the story that we write. We are going to beat the Chinese to the moon." Duffy's bold confidence isn't without foundation. Not long ago, he arranged a private meeting with the SpaceX HLS team, including CEO Gwynne Shotwell, to personally check whether their progress was truly on track. It came during a difficult stretch. SpaceX was struggling with setbacks from Flight 7 through Flight 9, while NASA itself was grappling with budget cuts and major staffing losses. What Duffy witnessed firsthand reassured him that NASA's $4.04 billion investment in SpaceX's HLS project was money well spent. Speaking to the press about Starship's recent troubles, he explained,
I talked to their leadership team yesterday, talked to Gwen. They feel very comfortable on Starship. They feel like they're on page for the lander, on track. So they feel very good. They said if there's a holdup for Artemis 3, it's not going to be them.
Later, after attending a Crew 11 launch attempt at Kennedy Space Center, Duffy doubled down. They, SpaceX, feel very comfortable on Starship. They feel like they're on pace for the lander. They told me if there's a holdup for Artemis 3, it's not going to be them. Sure, if Elon Musk had said this, it might sound overly optimistic, but when Gwynne Shotwell speaks, it usually carries weight. After Starship's 10th flight, the SpaceX president expressed pride in the achievement, while highlighting the company's long-term vision, sending hundreds, and eventually thousands, of people to the lunar surface to live and work. She declared, "Don't bet against American innovation." Flight 10 marked a turning point, helping SpaceX move past the so-called explosion curse. Earlier test failures, particularly Flights 7 through 9, had fueled doubts about progress. But with Flight 10's success, those concerns started to fade, restoring confidence in both NASA and SpaceX. The mission showcased critical milestones, including both stages executing controlled splashdowns, and most importantly, the upper stage successfully reignited its Raptor engine. These breakthroughs are vital for NASA's Artemis program, as they confirm essential Starship technologies required for human landing system missions to the Moon. Flight 10 also represents one of the final version 2 flights before SpaceX transitions to version 3, a design capable of reaching low Earth orbit for refueling and deeper space operations. Proving version 2's reliability is essential before moving forward, as version 3 will pave the way for human certification and ultimately make Starship HLS fully operational for Artemis 3. Before Artemis 3 can launch, SpaceX must first demonstrate that its Starship human landing system can both land on the Moon and lift off again. Initially, NASA's contract with SpaceX required only an uncrewed lunar landing. However, the agency later updated the terms. The demonstration must now also include a liftoff from the Moon's surface. This adjustment likely reflects the urgency of the Artemis schedule and NASA's effort to reduce risks ahead of the first crewed landing attempt. Under the revised requirements, SpaceX must complete an uncrewed demo mission, where Starship HLS touches down on the lunar surface, operates there for at least 2 hours, transmits data back to Earth, and most importantly, reignites its Raptor engine to launch off the Moon. In December 2023, NASA formally amended the Human Landing System Appendix H contract to include this milestone, but without providing any extra funding. For this test, Starship HLS isn't required to reach lunar orbit. The key criterion is simply proving a successful liftoff from the Moon after landing. Although SpaceX remains confident in Starship's progress, hitting every milestone required to support Artemis 3 in 2027 is shaping up to be a daunting challenge. As said, a series of setbacks has already slowed the program, pushing it well behind SpaceX's ambitious internal goals. As it stands, Starship is running at least 6 months behind its original schedule. Part of the difficulty lies in the sheer complexity of the system. Starship will require an unprecedented launch sequence and highly synchronized operations to make in-space refueling possible, something no one has ever attempted before. According to NASA, it could take 6 to 10 cryogenic fuel transfers to fully refill Starship's tanks for a lunar mission. Lori Glaze, NASA's Associate Administrator for Exploration Systems Development, has acknowledged delays in demonstrating cryogenic fuel transfer. NASA had expected to complete this milestone within the year, but progress has slipped, making it unlikely the agency will hit the 2025 target for fuel-to-ship transfer. One optimistic projection suggests SpaceX could begin uncrewed landing tests in the second half of 2026, following a successful orbital flight of Starship Block 3 in mid-2026. Still, neither NASA nor SpaceX has released an official timeline for the sequence of required launches. And even if all refueling and orbital logistics flights go as planned, a key question remains. Can a fully fueled Starship be certified for human spaceflight, safely land on the Moon, and return astronauts to Orion for the trip back to Earth. The Artemis program was launched in 2019 under former NASA Administrator Jim Bridenstine, with the ambitious goal of returning humans to the Moon. That same year, Vice President Mike Pence delivered a rousing speech in Alabama, setting a target of landing astronauts on the Moon by 2024 and laying the political foundation for Artemis. Today, NASA is aiming to fly around the Moon as early as February 2026. The mission's backbone relies on decades-old projects. The Orion spacecraft, first initiated in 2005, and the Space Launch System rocket, which began development in 2011. Together, these systems have cost more than $50 billion. Originally, Artemis II was supposed to launch in 2021, and the mission is not even as ambitious as Apollo 8 in 1968, which orbited the Moon. For Artemis III, the program's first planned lunar landing, NASA faces even greater challenges. It will need SpaceX to deliver a human-rated Starship, Axiom to provide new lunar spacesuits, and NASA teams to piece together and approve a complex, high-risk mission architecture. The official target for Artemis III is 2027, but as many experts point out, no reasonable observer believes that is feasible. For Acting Administrator Sean Duffy to keep his promise of putting Americans back on the Moon before the current president leaves office, that landing would need to happen before January 2029. If you're over 60, you were lucky enough to witness one of humanity's greatest achievements unfold live: the Apollo 11 moon landing.
It's one small step for man, one giant leap for mankind.
Hard to believe, but it's been 56 years since that electrifying day, July 20th, 1969. At precisely 2017 UTC, the world held its breath as Commander Neil Armstrong and lunar module pilot Buzz Aldrin took manual control of the Eagle. The landing site was rough, scattered with boulders, and their fuel was running dangerously low. Inside Mission Control, tension spiked. Engineers whispered, voices cracked, and time seemed to stretch endlessly. But it wasn't just Houston on edge. Living rooms across every continent were frozen in suspense, glued to their television screens. And then it happened. Armstrong's calm, steady voice broke through. "Houston, Tranquility Base here. The Eagle has landed."
Tranquility Base here. The Eagle has landed.
For a heartbeat, the world was silent. Then came the cheers, the tears, the pure relief. Humanity had just set foot beyond its cradle. A few hours later, Armstrong climbed down the ladder, and in that quiet moment, history was rewritten. His words still echo through time. That's one small step for man, one giant leap for mankind. More than a physical step, it was a leap of imagination, courage, and human spirit, proof that the impossible could be made real. Today, more than half a century after Apollo 11, history feels like it's echoing back, but this time with a bold modern twist. And if you've been following along, you know exactly what I'm talking about. No, not the grand return to the moon with Artemis III. That's still on track for mid-2027. I'm talking about the crucial stepping stone that just unfolded: Starship Flight 10. This wasn't just another test flight. It was the fourth launch of the upgraded Block II Starship, a version designed as the workhorse that will pave the way to the even more advanced Block III. Why does that matter? Because Block III is where the real magic begins. Testing in-orbit refueling, one of the toughest engineering challenges in space exploration. And here's the scale we're talking about. The ultimate design aims to carry 150 metric tons, over 330,000 pounds, of cargo to anywhere in the inner solar system. That's not just a rocket, that's an interplanetary freight train. But the pressure is real. After 3 tough setbacks since January, SpaceX is running out of chances with Block II. Only 2 more vehicles remain, including the one that just took flight. From here, all eyes shift to Block III, the version designed to finally reach orbit, refuel, and kick open the door to deep space. In other words, failure is not an option. The stakes aren't just high, they're cosmic. Fortunately for SpaceX, the fourth time really was the charm. In this latest test, they checked off nearly all the major objectives, making Starship Flight 10 the most successful mission of the program so far in 2025. And here's where it gets really poetic. This milestone didn't just happen on any day. The August 27th launch fell on the 6th anniversary of Starship's very first test. Back in 2019, the humble Starhopper prototype hopped just 150 meters into the Texas sky. That squat, water tower-looking craft didn't look much like the sleek Starship of today, but it was the first full-scale step into a new era. Fast forward exactly 6 years, and now we're watching a towering stainless steel giant fly higher, farther, and more confidently than ever before. That's not just progress, it's history coming full circle. The success of Starship Flight 10 didn't just lift SpaceX. It gave NASA a major boost as well. No one is paying closer attention to Starship's progress than NASA itself. In fact, shortly after the launch, NASA's acting administrator Sean Duffy posted a message congratulating SpaceX, calling the achievement a critical step toward preparing the Starship human landing system that will return American astronauts to the moon on Artemis 3. This isn't just a win for SpaceX, it's a milestone for NASA and all of its commercial partners working hand in hand to make humanity's lunar return possible. And this next chapter will be unlike anything we've ever done before. Back in the Apollo era, the goal was simple: land on the moon and return safely. But Artemis isn't aiming for a repeat performance. More than 50 years later, the mission is far bolder. This time, the target is the lunar South Pole, a region that could hold the key to humanity's future in space. Beneath the shadows of towering mountains and inside deep frozen craters lies something priceless: water ice. That ice could be turned into drinking water, breathable oxygen, and even rocket fuel, resources that could one day support a permanent human presence beyond Earth. But reaching this region is no easy feat. The South Pole is one of the harshest environments in the solar system. Jagged terrain filled with boulders, long craters that stretch for miles, and lighting conditions that make every step risky. The sun hovers low on the horizon, casting long shadows that can hide obstacles and confuse navigation. And those very same mountains that hold promise also block communication with Earth, making operations even more complex. That's why Artemis 3 is designed for longer stays, bigger payloads, and sustainable exploration. The technology we're bringing to the table is revolutionary, nothing like the Apollo era's single-use landers. At the heart of this new chapter stands a masterpiece: the Starship HLS. Unlike Apollo's lunar module, which could only make one trip, Starship HLS is being built for multiple missions. It's a colossal spacecraft equipped with advanced Raptor engines, an innovative docking system, and even an elevator to carry astronauts and cargo from the ship down to the moon's surface. With its ability to transport larger payloads, support extended surface missions, and be reused across multiple expeditions, Starship HLS represents a fundamental shift in how humanity approaches deep space exploration. And here's the connection that makes today's achievements so powerful. The Starship flights we're watching now, every launch, every failure, every breakthrough, are laying the groundwork for that future. What SpaceX is proving today will form the backbone of the Starship human landing system tomorrow. In other words, when astronauts step onto the moon again, they won't just be standing on the shoulders of Apollo, they'll be standing on the shoulders of Starship. But while the United States is pushing forward with Artemis and Starship, there's another layer to this story: the geopolitical race back to the moon. And make no mistake, urgency matters. Because America isn't alone this time. China, the new contender in the space race, is moving fast, very fast. Despite entering the game decades later, China has built an ambitious lunar program with a clear timeline: land astronauts on the moon before 2030, and begin constructing an international research base there by 2035. The technologies they're rolling out are no less impressive: the Long March 10 heavy rocket, the Mengzhou crewed spacecraft, advanced lunar landers, rovers, and even a full suite of systems designed to sustain human presence on the moon. And the progress is already visible. In August 2025, China achieved a milestone of its own: the first landing and takeoff test of its Lanyu lunar lander. Inside a specially built facility designed to mimic the moon's surface, complete with craters and soil like regolith, the lander successfully demonstrated both descent and ascent. It's a critical capability: one module designed to land with descent engines, the other to lift astronauts back off the lunar surface. That means China is now testing the exact technology needed for a crewed lunar landing. And this isn't happening in isolation. Over the past few years, China has been steadily building up experience through a series of robotic missions. Chang'e 5 in 2020 and Chang'e 6 in 2024 brought back precious lunar samples, giving scientists direct insights into the moon's geology, especially around the South Pole. And the pipeline is far from over. Chang'e 7 in 2026 and Chang'e 8 in 2028 are designed to explore the lunar South Pole for resources, testing technologies for in situ resource utilization, and laying the groundwork for a sustainable lunar base. Meanwhile, China has teamed up with Russia to propose an ambitious project: the International Lunar Research Station. Planned in phases through 2035 and beyond, this base would be a multinational outpost on the moon's surface, acting as both a research hub and a permanent foothold in deep space. On the other hand, the US isn't falling behind. In fact, some of the most critical technologies for lunar exploration are already being tested. During Starship Flight 3, SpaceX pulled off something subtle but groundbreaking. They transferred liquid oxygen between two tanks inside the same Starship in orbit. It might not sound dramatic, but it proved one of the hardest parts of deep space travel: that cryogenic fuels can be handled and moved around in the weightlessness of space. From there, the roadmap only gets bolder. The next big leap will be the Starship propellant transfer demo, targeted for 2026. This will be the first time SpaceX attempts a full demonstration of in-orbit refueling, launching two Starships just weeks apart, one acting as the tanker, the other as the receiver. If successful, it will unlock the ability to fuel up in low Earth orbit before heading to the Moon, Mars, or beyond. And this is where America's advantage becomes clear. SpaceX has a track record of relentless innovation, pioneering things like reusable rockets, stainless steel super heavy boosters, rapid launch turnaround, and now scalable in-orbit refueling. These are not technologies you can simply reverse engineer or copy. They come from years of trial, error, and iteration. For China, those breakthroughs remain out of reach without SpaceX's permission, collaboration, or their own decades-long grind of experimentation. Of course, NASA isn't putting all its eggs in one basket. While SpaceX drives Starship forward, Blue Origin is quietly carving out its own path in the Artemis program, particularly in the area of in-orbit refueling and lunar transport. One of their most promising projects is the Blue Ring Space Tug, a versatile vehicle designed to provide transportation and refueling services not only in Earth orbit, but also in cislunar space near the Moon. Blue Ring can haul significant payloads, deliver satellites, or act as an orbital gas station, offering the maneuverability and delta-V needed for missions that push deeper into space. The technology isn't just on paper, it's already being built and tested. The prototype, called the Blue Ring Pathfinder, or Flight Vehicle 1, is currently moving through a critical assembly phase. This test spacecraft was launched aboard the inaugural New Glenn rocket on January 16, 2025. Affixed to the rocket's second stage It was placed into medium Earth orbit to demonstrate Blue Ring's transfer and refueling capabilities in real conditions. By mid-August, Blue Origin announced an important milestone: the successful stacking of the aft and forward propulsion modules of Flight Vehicle 1 inside the Propulsion Integration Tool, a system that guides installation and secures the modules into their final configuration. Next steps include intermodule welding, acceptance testing, and integration with the vehicle's primary flight structure. In other words, the prototype is quickly taking shape. And that's not all. No earlier than late August 2025, Blue Origin plans to launch the Blue Moon Mark 1 Pathfinder mission, a robotic lunar landing demo that will act as a full dress rehearsal for bigger ambitions. Think of it as a shakedown cruise, paving the way for the far more capable Mark II lunar lander. That lander isn't just a test vehicle, it's the design slated to carry astronauts to the moon as part of Artemis 5 in 2030. On Wednesday, September 3rd, SpaceX's Dragon spacecraft captured global attention as its brand new propulsion system successfully demonstrated, for the very first time, its ability to help the International Space Station maintain its orbit around Earth. The ISS periodically requires these boosts because trace amounts of air in the upper atmosphere gradually slow it down. Without such pushes, the station would slowly descend closer to Earth. Until now, this critical job had been almost exclusively handled by Russia's Progress vehicles and the station's built-in thrusters. That's why Dragon's successful reboost marks a major milestone, signaling greater U.S. independence in a task long dominated by Russian spacecraft. To pull this off, Dragon has been outfitted with an advanced boost kit that includes 2 powerful Draco engines containing an independent propellant system, along with heaters and insulation, all carefully tucked into the spacecraft's trunk. The upgrade gives Dragon 1.5 times more thrust than a Russian Progress vehicle, and that power was on full display during its latest test. A burn lasting just over 5 minutes that lifted the station's orbit by about 1 mile. This achievement has boosted NASA's confidence to schedule Dragon for multiple reboosts throughout fall 2025. By then, Dragon is expected to take on the majority of the ISS's orbital maintenance while docked, a huge leap beyond the limited 1 or 2 burn routine offered by Progress. NASA specifically assigned SpaceX this role as part of a broader, long-term vision for the future of the station. The data gathered from Dragon's orbital boosts will directly support the design of the U.S. deorbit vehicle, an advanced evolution of Dragon's platform. This future spacecraft will ultimately be responsible for ensuring the safe and controlled re-entry of the ISS when its mission in low Earth orbit concludes, likely around 2030 or 2031. The uncrewed Dragon spacecraft used for this mission was C211, which launched on August 24 as part of the CRS-33 cargo resupply flight to the ISS. It will remain docked with the station until around December or January before returning to Earth with valuable science samples and cargo. Although this marks the first trial of Dragon's upgraded propulsion system, it's not the first time a Dragon has attempted a reboost. During the CRS-31 mission last November, another cargo Dragon, C208, ignited its capsule-mounted Draco thrusters for a 12.5-minute burn. That maneuver slightly adjusted the station's orbit, raising it by about 0.11 kilometers at the highest point and 1.1 kilometers at the lowest. Typically, those Draco thrusters are meant for maneuvering and attitude control, not for boosting the station itself. While the test was successful, it wasn't an ideal solution since the thrusters weren't designed or positioned for that purpose. Instead, it served as a proof of concept. Could Dragon actually step up to the task? Dragon's new capability to boost the ISS can be seen as the well-earned reward of SpaceX's years of experience in safely and reliably docking the spacecraft with the station. Since the first cargo mission in 2012, Dragon has been coming to the ISS for over a decade. Each time it docks, Dragon carefully attaches itself to the station to deliver food, experiments, and equipment to the astronauts inside. Over time, NASA and SpaceX have learned how to do this docking smoothly and safely many times. Because Dragon is already so good at connecting to the ISS and staying attached for weeks or months, engineers realized they could add special thrusters, small engines, to Dragon that let it push or boost the station's orbit while it's docked. This is a big new step, but it's possible because Dragon's history with docking gave them the skill and confidence to try it. Of course, successfully boosting the ISS's orbit isn't the only major leap for a space docking pro like SpaceX. On September 3rd, Elon Musk revealed that 2026 is shaping up to be a breakthrough year for Starship, with multiple in-orbit refueling tests planned using the upcoming Starship version 3 rocket. The fascinating part? These tests will involve refueling Starship while it's floating in space by docking it with another Starship, a maneuver Musk describes as docking with ourselves. Even more intriguing, he pointed out that this maneuver will actually be a much easier challenge than docking with the ISS, something Dragon has been doing reliably several times a year. Musk's optimism about Starship's ability to fully demonstrate in-orbit refueling technologies by 2026 has solid grounding. During Starship Flight 3 last year, SpaceX successfully transferred around 10 metric tons of liquid oxygen from header tanks to main tanks while in space. This tank-to-tank test validated how fluids behave in microgravity and was considered a NASA-funded success, even though it was conducted within a single vehicle. By August 2025, Starship had completed 10 orbital flights, concentrating on ascent, re-entry, and soft landings. The 10th mission, flown on August 26th, was the first successful flight for the Starship version 2 vehicle. It achieved all major test objectives, culminating in controlled splashdowns of both the Super Heavy booster and the Starship itself. SpaceX plans one more flight with this version before transitioning to version 3 launches from Pad 2. Starship version 3, a major leap from the current version 2, is expected to wrap up production and testing by the end of the year, according to Elon Musk. Its high flight cadence is set to kick off next year. Block 3 comes with significant hardware upgrades, including Raptor 3 engines, enhanced docking ports, quick disconnect systems for propellant transfer, and better insulation to minimize boil-off. Together, these improvements allow for longer orbital loiter times, up to 3 to 4 weeks, crucial for carrying out complex refueling sequences. However, several challenges still lie ahead. First and foremost is ensuring rocket survivability from launch to landing. This is an essential interim goal that must be achieved before engineers can move on to bigger milestones, like in-orbit refueling. Starship needs to consistently survive both launch and landing to validate the latest improvements to its heat shield. Second is addressing propulsion and fueling issues. Some of this year's Starship setbacks with version 2 were tied to problems in these systems, and in June, another Starship even exploded on the test stand. For in-orbit refueling to work, propulsion and fueling systems must be exceptionally reliable to carry out the complex, precise maneuvers required. Last but certainly not least are rapid reusability and in-orbit refueling. Former NASA Administrator Jim Bridenstine highlighted that rapid reuse is critical for orbital refueling because it allows multiple fuel deliveries within a short time frame, avoiding the long waits that would come from building and launching new rockets each time. Fast turnaround drastically reduces costs, making spaceflight more affordable and sustainable. Without rapid reusability, refilling spacecraft in orbit would be too slow and prohibitively expensive, ultimately slowing exploration efforts. For SpaceX to achieve this, Starship must return from orbit with its heat shield in excellent condition, ready for another flight. On top of that, the ambitious Mechazilla catch system must work flawlessly for both stages. While SpaceX has already demonstrated the ability to catch the Super Heavy booster, the challenge now is Starship itself. Elon Musk has predicted a tower catch for the upper stage within as few as 3 more flights, marking a major upcoming milestone for the program. As for cryogenic in-space refueling, Breitenstein cautioned that this remains an undeveloped, highly complex technology. In his words, "Our complicated architecture requires a dozen or more launches in a short time frame, relies on very challenging technologies that have yet to be developed, like cryogenic in-space refueling, and still needs to be human-rated." In testimony before the U.S. Senate Committee on Commerce, Science, and Transportation, he warned that although Starship's payload capacity could be revolutionary, its current complexity precludes alacrity, leaving the U.S. at risk of falling behind China. Similar concerns extend to Blue Origin's Blue Moon Mark II system, planned for Artemis 5. Like Starship, Mark II depends on multiple cryogenic propellant refuelings through its cislunar transporter. While still unproven, successful refueling would open the door to heavier payloads, up to 30 tons in a one-way mission, or 20 tons in a reusable configuration. However, with SpaceX's rapid progress and its mastery of space docking, it's hard not to believe the U.S. is gaining a real edge in the new space race. What do you think? Are we watching America's path to victory unfold? If you agree, drop a 1 in the comments. Anyway, the absence of a ready lunar lander isn't the only obstacle facing the U.S. in the second lunar space race with China. Jim Bridenstine has underscored the high costs and sustainability problems tied to NASA's Space Launch System, SLS, labeling it extraordinarily expensive. Since its inception in 2011, SLS development has cost around $23 billion, with additional billions poured into Orion and ground systems. Each Block 1 launch comes with a price tag exceeding $2 billion, before even factoring in long-term amortization. Planned Block 2 upgrades push the costs even higher. A key driver of these expenses is the cost-plus contracting model, which often incentivizes delays and overruns. Boeing, one of NASA's primary contractors, has been at the center of many of these issues. As the lead for the SLS core stage and the interim cryogenic propulsion stage, ICPS, Boeing has faced heavy criticism for mismanagement, underestimated workloads, workforce challenges, and technical hurdles in both hardware and software. Core stage delays alone added about 2.5 years and $4 billion in extra costs. On top of that, Boeing struggled with supply chain problems, infrastructure setbacks, and even tornado damage at the Michoud assembly facility. Northrop Grumman, tasked with building the solid rocket boosters, also encountered problems, including defects in the booster's propellant liner and insulation. Frequent contract modifications complicated oversight and added administrative burdens. Technical issues with new components further delayed progress. Aerojet Rocketdyne, responsible for the RS-25 engine's new controller unit, has also slowed the program. Development ran into faulty memory chips and complex testing requirements, delaying engine certification and pushing back the SLS launch schedule. The rocket's high per-launch cost is worsened by its expendable design. Each mission requires a brand new core stage, solid rocket boosters, and RS-25 engines. This approach caps the launch rate at just 1 to 2 flights per year, currently estimated at once every 18 to 24 months. Such a limited cadence is unsustainable for NASA's Artemis ambitions, which call for frequent missions to support a lunar base or eventual Mars exploration.
You got all these sensations coming together. You're cold. We were really cold. You're using 2/3 of your oxygen supply is being used to cool you.
The very first thing the Polaris Dawn crew noticed about SpaceX's brand new EVA suit wasn't the view, or even the thrill of floating in space. It was the cold. And not just a little chill. Jared Isaacman and his team were shivering uncontrollably inside those futuristic suits. So what was going on? The culprit was the suit's cooling system. It pumped 2/3 of the oxygen they breathed through a special vent. This vented oxygen helps keep their temperature down, but it can also make them feel very cold when outside in space. Isaacman believes this wasn't an accident, but an intentional move by SpaceX engineers. Why? Because back in the 1960s, during Gemini missions, overheating was a nightmare. Astronauts would come back from spacewalks drenched in sweat, exhausted, and barely able to re-enter their capsules. SpaceX seems to have taken the opposite approach. Better to freeze a little than to cook alive. In other words, the crew may have been uncomfortable, but the system did exactly what it was designed to do: prevent the kind of heat-related failures that plagued early spacewalks. The problem now? Finding that perfect balance between too hot to handle and too cold to function. The second big challenge? Mobility, or rather the lack of it.
You got all these pressure, changes and sensations because we were operating at 5.2 psi. You've got exertion because you're working against a suit at 5.2 psi.
SpaceX's EVA suits were designed to operate at 5.2 psi, roughly 1/3 of Earth's atmospheric pressure. That's enough to keep astronauts alive in the vacuum of space. But it came with a brutal side effect. Movement felt like a full-body workout. Jared Isaacman described it as a constant battle against the suit's internal pressure. Every arm raise, every leg extension, even the simplest motions demanded deliberate force, like pushing against an invisible spring. Think of it this way. Imagine trying to jog or climb while wearing an old-school pressurized diving suit on land. Sure, it keeps you safe, but it also makes every step exhausting. That's exactly what the crew faced out there. So how did they manage? Luckily, Isaacman wasn't floating aimlessly. SpaceX had equipped Dragon with a clever piece of hardware nicknamed the Skywalker. This was essentially a metal framework that replaced the usual docking mechanism, giving astronauts handholds and anchor points to grab onto. With it, Isaacman could perform structured mobility tests instead of flailing against the suit's resistance. The takeaway? SpaceX's EVA suits worked, but they turned every move into resistance training. The Skywalker was less of a luxury and more of a lifeline. This rigidity ties into issue 3, Dragon hatch, malfunction.
So they built this automated hatch motor. It probably took like 6 to 9 months to do it. And then a couple weeks before we launched the mission, they're like, hey, we've been running some numbers and we don't think it's going to work. We think there's going to be enough residual pressure coming out of your suit, venting from your suit, across the surface area of the hatch that it's going to overpower the hatch motor. So you may need to do it manually.
Originally, SpaceX engineered an automated hatch closing motor for the Dragon capsule. But weeks before the September 2024 launch, they hit a snag. When Isaacman vented his suit's residual pressure, it risked overloading the motor. Cue the last-minute pivot, Isaacman had to manually crank the hatch closed. He emphasized SpaceX's push to minimize human intervention, making this a humbling, hands-on fix. Now it's important to remember, what Jared Isaacman and his crew wore on Polaris Dawn wasn't the final product. That EVA suit was Generation 1, a proof of concept. Since then, SpaceX has sprinted ahead, and by 2025, they'll have already developed 2 more generations, each iteration pushing closer to the kind of suits astronauts will eventually need on the Moon or Mars. Isaacman himself called the original version a minimum viable product, but he never spoke about it with frustration. Instead, he showed gratitude. Why? Because that first-gen suit represented an incredible engineering achievement. It was built in just 2.5 years by SpaceX's in-house team, a team that leaned heavily on NASA's decades of spacesuit heritage to jumpstart their own design. The new EVA suit takes its roots from the pressure suits astronauts already wear inside Crew Dragon, but it's been transformed. It's designed to be lightweight, unobtrusive, and to protect astronauts in the most hostile environment imaginable. As SpaceX principal spacesuit engineer Eric Krause put it, it's kind of like a suit of armor made of fabric. And SpaceX has been stacking innovations on top of that foundation. New flexible joints give astronauts more mobility, while the helmet and visor come with a built-in heads-up display that feeds them vital telemetry, pressure, temperature, humidity, all without blocking their view. For safety, the visor is made of tough polycarbonate, coated with copper and ico, or indium tin oxide. Together, these layers bounce sunlight away while reflecting infrared heat back when astronauts are turned toward deep space. The suit also features a Faraday layer, a conductive cage woven into the design to shield astronauts from dangerous external electric fields. And when pressurized, the soft fabric portions of the suit stiffen like armor, supported by specialized flexure and rotational joints so astronauts can still move with precision. Another major hurdle: thermal comfort. SpaceX senior spacesuit manager Chris Trigg explained that the suit has to handle extremes: intense solar heating on one side, freezing darkness on the other side, all while keeping the inside safe and comfortable to the touch. And perhaps one of the most impressive aspects: the suit is designed and manufactured right in Hawthorne, California, almost entirely in-house. To speed up production and future scalability, SpaceX even developed a new fabric-based material that makes building these suits faster and more efficient. But Jared Isaacman didn't just share what it was like to become the very first person to wear SpaceX's brand new EVA suit. He also opened up about something even rarer: the surreal feeling of floating 740 kilometers above Earth. Imagine stepping outside a spacecraft, floating in the raw emptiness of space. Jared Isaacman described the experience as holistic, a word that barely scratches the surface of what it meant. He was strapped in, tethered, and hyper-aware of something astronauts had learned as far back as the 1960s. You can't build or repair anything in space if you're just drifting. Every move relies on secure contact points because in microgravity, control is survival. The whole EVA sequence, from vacuuming the capsule to bringing the air pressure back, lasted around 2 hours. But Isaacman himself was outside for just 8 minutes. And yet, in those 8 minutes, time bent in strange ways. Inside or outside, minutes slipped away in a blink. As the hatch was about to open, a rush of thoughts hit him.
And then when I was getting ready to open the hatch was just, don't F this up, man. Like, it's just like, you don't want to screw up. You don't want to let everybody down who got to help you get to this moment.
Originally, the team trained on manually closing the spacecraft's door, a skill from the early days of spaceflight. But later, SpaceX added an automatic motor to take over that job. Then, just weeks before launch, a curveball. Engineers discovered Isaacman's suit pressure might actually overpower the motor. Suddenly, manual door ops were back on the table. In the end, he opened the door himself. And for him, that was very cool. Because it wasn't just the system, it was him. And then came the view. At first, only a pitch-black void swallowed his vision, an unsettling nothingness. But the moment he shifted and turned toward Earth, the planet exploded into sight beneath him. He only had a few minutes before the craft drifted into the orbital danger zone, where maneuvering tests forced them to turn away from Earth. Looking into that endless dark, Isaacman felt a chill of unease. He compared it to 15th century explorers staring into the unknown, knowing danger lurked just beyond the horizon.
It definitely was what I was feeling was like a very unsettling, like almost it's a threatening environment. Like, we don't know what's out there, but it's all very hazardous to us humans, and proceed with caution. Kind of like the explorers in the 1400s, like, I may sail off the end of the Earth because it's flat, or there might be a monster there waiting to eat me, but I'm still going anyway. And that was kind of the feeling I had looking out into the darkness of space.
At that moment, he was flying over the South Atlantic, near Antarctica, where radiation levels spike higher than almost anywhere else in orbit. It was so intense that his heart rate monitor malfunctioned. When the time came to return, frustration set in. He wanted to stay out longer, to soak in every second. But crew member Sarah Gillis was still outside, in the high-risk zone, unable to see Earth at all, and he didn't want to eat into her time. After repressurization, the crew noted the sharp smell of nitrogen and fresh oxygen filling the cabin. They were shivering. It was freezing inside. The mission wasn't Isaac Manns alone. Alongside him were Kid Pott, Sarah Gillis, and Anna Menon. Together, Gillis and Menon achieved something historic. They became the farthest women ever to travel from Earth.